Irina Popkova for allowing me to change slot with her. And so I understand it's my final slot, so but I won't be long because I have hard stop anyway at 10 o'clock local time. So again, I wish I would be in Turkey again. I planned to come, but unfortunately it didn't happen at the end. So I wish I will be standing next to you guys. So anyway, so today I will be talking about high density memory based on stuck magnetic and Josephson junctions. The work is done by Ivan Niverkovets from Northwestern University, who also are consulting for us, and SEEK is a company, new company, which spun out from Hypress and located in the same area where Hypress used to be. In fact, in the same building and also next building to it. So it's in New York area. Let me talk about dry memory problem. And it's a little bit busy slide, but what I would like to tell that first of all, if look at the left panel where I summarized sort of status today. So despite of a lot of very nice and excellent results in physics and materials, especially on ferromagnetic junctions and so on and so forth, there were no yet random access memory developed. So you cannot have it, you cannot use it, just not done. And as you know, there was a lot of big effort in the US in particular. C3 project was funded a few groups to develop random access memory, but result was, again, significant progress in the device, on the device level, but no memory. And the reason is that in order to build memory, which would be useful, you have to pay attention to the right panel, where in green, I try to summarize what kind of requirements are needed in order to really build something useful out of these wonderful devices. The memory element, when most of the people focused on memory element, but it's definitely not enough because you need to have memory element to be arrayed in addressable. Addressable is the key word here. Random access memory array, and it has to be dense. So therefore, the pitch or distance between different memory cells, neighboring memory cells, should be minimum. So it means that not just memory cell is small, but also the distance to the next cell should be small. And as I mentioned, the addressable word is the key here. It should include some means to read out the data stored in the memory, and also have efficient ways to erase and record data into this element. And because it's a cryo memory, it should not, the energy efficiency is very important because you need to put it in cryogenic environment where capacity for lifting heat is limited. So therefore, it shouldn't burn energy in non-selected cell. When you address it, you shouldn't burn energy in the lines, so they have to be superconducting and so on and so forth. And it has to be fast. So you would like to read it very fast, like in picosecond, and write, you can afford to have somewhat more time for that, because at the end of the day, you would like to integrate it with digital circuits, which exist in cryo world, which is single flux quantum electronics. All right. So what do we have now? First of all, let's look at semiconductor memories because they are available. You can buy them. They're being developed new and new. And the reason that they are so successful because they have 3 terminal devices, which being used as a cell selectors, memory cell selectors. So still, if you take a usual MRAM, right? Magnetic random access memory. It has a two-terminal device, but in order to make it addressable in the array, it always integrated with a CMOS transistor under, which located usually under the cell in a stacked fashion. So you have CMOS, and then on top you have this memory. I would call them storage elements. It could be MTJs or what have you. So you always have that integrated together. So that's why this memory are so successful. Unfortunately, in JJ technology, such three-terminal devices are not available. So JJs are also two terminals. So people can use maybe something more than that. For example, squids or entrons. But if you compare squids or entrons, they are quite big. So compared to, let's say, magnetic Josephson junctions, they are orders of magnitude larger. So therefore, what we have memory which the best superconductor, totally superconductor memory based on just conventional SIS junctions. I have memory cell about 100 micron square, so which means that probably 0.9 megabit per square centimeter you can get. But again, this is just a try memory. It's a demo memory. It's not real memory that people can use, but it just shows that you can densify. Still, it's orders of magnitude more than you have in semiconductor industry. So therefore, I would say what to do. That adding ferromagnetic junctions, as it was already many people working on it, it's a good thing because it's expanding toolbox, it's adding elements which can store information just in the junction itself. So this is really fast to good memory. All right, so what we offer here. So we decided that the best way is to try to integrate a sense element and a storage element together in a stacked fashion. So that's how this device looks like. So you can see on the left, I don't know whether you see my pointer. Let me see. Where is it? All right, so you see the magnetic junctions is on top, which has this free and fixed layer, which you can change magnetization. And then you have SIS junction at the bottom. And this is it's not a one device, it's kind of two junctions put on top of each other. And as you see, lithography done was different. So one junction is clearly larger than another. And I will tell later why this is important. And and also what you can notice that because they are different size and done sort of with different lithography, you're able to connect electrodes in the middle. So you can, between them, you can connect electrodes, you do your wiring. So in fact, what you create here, you create multi-terminal device. So you see, despite that each junction is two-terminal, because of this strange configuration, we're able to kind of turn it into a multi-terminal device. So which, as I will show you later, will enable more functionality when you array memory. All right, so what materials do you use here? The SAS junction is conventional. It's niobium, aluminum oxide, niobium. The magnetic junction is nickel is a fixed layer and permalloy is a free layer. So very kind of conventional layers. I wouldn't say anything sort of super unusual here. On the right panel, you see sort of micro photograph of the device. So you can see top electrodes and middle electrodes. So you see that we able to connect wires to this middle electrode, and that is very important. This is crucial, in fact, for making good memory. All right, so this is characteristics of this devices. So first, you on the left, you look at conventional sort of the magnetization curve, and they again look very traditional. So you see that between in the area which designated in total about 9 millitesla, you see rotation of the thermaloid, the free layer, and then of course if you go beyond 20 plus minus 20 millitesla, you see that fixed layer also can be rotated. So this is again very much conventional as expected characteristic. Now let's look at the right panel, and you look at the characteristics of the SIS junction, which is sensing element for this in this device, and you see that for parallel and anti-parallel magnetization of the MTJ, you see different critical currents, and also critical currents when it's suppressed, when it's in parallel configuration, it's sort of shifted to the right. So this is two different current field characteristics based on the magnetization state of the MTJ. So which is indicative that with SIS junction, you can sense what's happening in MTJ. So now let's look at what actually happening there. So let's see what we're trying to achieve in this multi-terminal stack device. First, look at the A on the very left, and you see anti-parallel configuration. So magnetic field will be confined between these two layers. So it really doesn't propagate much because it's quickly sort of goes from one ferromagnetic layer to another. And however, if you put in parallel configuration, this is in the middle, the B. So we see that magnetic field expands, and what is more important, that it goes through SIS junction especially on the periphery of the device, right? Basically, in this extra area at the band around the MTJ, if it's overlapped with SIS junction. So you see that it's vertically penetrates SIS junction. So that's where suppression of critical current of junction happens. So that's why this band around MTJ is very important in order to, the more you have in relative terms of this area, the more critical current will be suppressed. In this particular case, its suppression is not that large, but again, it can be larger if you optimize your circuit. And in some samples, it was up to 30%. So now, basically, the takeaway from this slide is that what you're doing here, and this is very important, very different compared to what people were normally trying to do. For example, again, recalling C3 program, they're trying to optimize devices to increase MR, magnetic resistance, the difference between in resistance between parallel and anti-parallel. They're saying we don't do that. We don't need to do this optimization. What we're trying to do, we're not trying to sense magnetic resistance. We don't care about it. We care about local magnetic field. That's what we would like to sense, and that changes the whole optimization. Now let's see whether we can array these devices into a matrix which would be fitting to the criteria of RAM that I showed you before at the very first slide. So this is a little bit confusing, perhaps, picture, But let me explain. So each element is this stack junction where MTJ is on top and SAS at the bottom, and because you have the SIS somewhat bigger, so you can have contact to the top electrode of SIS junction. So if you look at this IR current, so you can apply current directly to SIS, and then from top electrode and from bottom electrode you can connect to another. So in the row, if you take a particular row in this matrix, you see that you can serially connect SIS junctions in the circuit. So what it means that if you apply this particular current, it only flows through SIS junction. It doesn't flow through MTJ, which is resistive, obviously. It only goes through the superconducting path only through SIS junction. So what it means that if you apply this current, you don't burn energy unless this SIS is resistive. Then this rows, so pink and green line, they are overlapped on top, and this is just very conventional field programmable configuration in order to change magnetization of MTJ. You do it using not spin torque, but just very plain vanilla field programmability. And of course, there are some advantages or disadvantages of such programmability, such function, but at the same time, if you use, for example, spin torque, you have to run current through MTJ and you burn energy. So you run current through, in array, you have to run current through entire column or row of MTJs and you burn a lot of power. And there were also work on spin Hall effect where current, in order to do spin torque, spin Hall effect kind of rotation, you have to run current through heavy metal and you burn even more power. So that's why just field programmability, when you use superconducting lines and you run current totally lossless through lossless passes, is good because it allows to not to burn power where you don't want. All right, so operation, as I pretty much already explained, that what you do, you just do exercise field programmability, you have these two lines and you combine them in such a way that only in the element which is in the middle, the currents will be combined properly, go over the threshold, rotate free layer, and you get your information written in. So let's talk about read operation. Read operation is a bit trickier. And as I said, we're focusing not on reading out MTJ or MR or what have you, we're reading out the local magnetic field. So what we do, we need just to look at the critical current of this readout junction, which is integrated beneath of MTJ. So these are, again, characteristics of this SIS junction. And so let's look at first at the solid black and solid right lines. And as I showed before, the changing in magnetization of MTJ, what it will do, will suppress critical current and shift it to the right. So that's what it is. So that you saw before, that's what we can observe. Now, we apply current, for example, IY current, which writes additional field into the particular column of the cells. So when you apply it, you provide additional sort of field which shifts everything to the right. So you see, when you do that, you have dashed lines for P and AP configuration. So now what you need to do in this sort of half-selected column, you need to look at the difference of these two lines, and when it's crossing sort of the zero field X. All right, so I'm pretty much done. So here's the characteristic of read. So what it shows that you can actually do that with SAS. So let's go to our last two slides. And first is, again, I'm not going to read it all, but I'm just showing that this, based on the already demonstrated results, even with very modest lithography, you can build pretty much very dense memory. And you can optimize it further in order to create more margins. But this is not something that you need to develop, put a lot of money into developing the fabrication process. Even with very much conventional materials and processes, you can get something working now. So, and my final slide is comparison to the requirement, which I showed you before. So let's see whether we can meet these requirements. And first of all, you can array a random access memory, so you can put it in addressable and dense memory. And again, field programmability, of course, will compromise a little bit density, so you need to make sure not to create crosstalk or other cells, but again, people in semiconductor done that. So each cell already includes sense element, and we know how to write and erase information, and everything done through lossless superconducting lines, so you're not burning extra energy anywhere. And yeah, and as I mentioned, the readout information done through reading the local magnetic field, not MR, so that makes headaches in optimization circuits a lot easier. And it's can be done fast because SAS junction is fast, so you can read it out pretty quickly. And MTJ, the remagnetization of MTJ can also be, again, as C3 showed, program showed, can be done within 100 picoseconds or so. All right, so with this, I'd like to conclude, so you can take any question. Depends on mostly economic issues, whether you have a program, because our company focusing on quantum computing, but quantum computing assisted by classical superconducting electronics, so it's integrated actually. So memory is needed. It's not, however, it is not on sort of near-term priorities. So if it will be a good program to do that, we will build it. As I showed, it doesn't appear to be very difficult. Of course, optimization can be done to make it better and better, but at least something can be done near term. So we kind of seeing whether we can allocate time and people to do that. But it's not, I would say currently it's not being done. It's more patent and proposal at this point. Patented.
Thank you. Mm-hmm. We hope. We hope.
Yeah, I hope too. Yeah.
Yes.
Hello, Oleg. This is Thomas.
I also like to ask a question. You mentioned a fast read is possible, but how about the right times and about the right current you need?
Again, it's a field programmable, so you need to apply currents, and you need to make sure that it's coupled appropriately to a particular cell. And of course, the smaller cell, the coupling will be less, although the amount of current that you need to apply is also reduced. So it's again optimization problem. And if we learn from C3 project, where we also investigated not just pin-torque but also the field programmability, it ostensibly can be done within hundreds of picoseconds. I put bravely 100 picoseconds, less than 100 picoseconds, but again, it could be 200, 300 or something like that. In the context of applications that we care about, this is again in control of quantum computers. It will be primarily the slow write is okay. Read should be fast, but it would be slowly programmed. That's acceptable for this particular application.
Yes. Do you also have an estimate about the write current?
Not at this moment. It's as I mentioned, will be dependent on the area of the cell and MTJ and the coupling coefficient that you can apply. But again, based on what we've done with memories before, I don't expect that it will be much different from that. So therefore, conventional line drivers that people do for memories, for speed-based memories, would be of the same order.
Okay, thank you very much.